All right, here's chapter 6, Energy and Chemical Change, based on the Jesperson text. So in this chapter, we're going to be looking at the difference between potential and kinetic energy. I'm sure most of you have that under control already, but again, we'll cover it just to make sure. We'll look at the principle of the conservation of energy. We'll look at the connection between energy, heat, and temperature. We'll learn about state functions, and then we'll determine the amount of heat exchanged from the temperature change of an object. And then we're going to try to understand exo and endothermic reactions. After that, we'll learn to apply the first law of thermodynamics, understand the difference between heat of a reaction under constant pressure versus constant volume, explore the utility of and assumptions in thermochemical equations, and then we'll get to Hess's law and be able to predict the enthalpies of reaction, and then use the standard heats of reaction to solve problems. So obviously the chapter is going to be based on thermochemistry. Thermochemistry is the study of energies given off or absorbed by reactions. We call that thermodynamics. So thermodynamics then is the study of heat transfer or heat flow. So basically we're going to look at how objects obtain heat and how they get rid of heat or release heat. And we'll look at that from an energy point of view. So we know energy is capital E, and energy is the ability to do work, or in our case, to transfer heat. Kinetic energy then, Ke, you probably know is the energy of motion. In your physics course, I'm sure you've learned that it's 1/2 mv squared. We'll take advantage of this, but we won't be using that equation in our course outside of using it to derive concept. So for potential energy then, it's going to be stored energy. It exists in natural attractions and of course repulsions, things such as gravity, positive and negative charges, springs, things of that nature. For chemical energy, the potential energy is possessed by the chemicals themselves. Right? So you can think of the little molecules as being little batteries. We can store that energy in their chemical bonds. And so now breaking bonds will require energy. And then so that might think, well, then we would never have reactions. But on the other side of the reaction, remember, we'll be forming new bonds, which typically is going to be releasing energy. So now, if the new reactants release more energy than the old bonds contained, then we'll see a exothermic reaction. And we'll get into the details of that a little later. But that will be another driving force for our reaction. All right, so which of the following is not a form of kinetic energy? So a pencil rolling across a desk, sharpening the pencil, heating up the pencil just sits on the desk, or the pencil falls to the floor. And hopefully you said when it's just sitting at rest. All right. What are some factors that can affect potential energy? So here we're going to be looking at electrons and nuclei. We have a low potential energy for atom A. And of course, this would be based on the distance, right? So an increase in potential energy, if we pull apart objects that attract each other, that's going to cost us, right? That's going to then increase the potential energy because they're going to want to pull together, okay? A book is attracted to the earth by gravity. And of course, if we take magnets, this is probably easily seen. North and south poles of magnets, if I try to push those near each other, they repel or they attract, right? So in this case, north and south would attract, opposites attract. And so if I'm trying to pull them apart, then that means the attraction is going to be strong and then slowly weaken out, right? Positive and negative charges then, such as the nuclei with our electrons. And of course, we can push together objects that repel each other. That will also increase that potential energy. So a spring is compressed, or if we take the south and south end of two magnets and push them near each other, they start to repel, right? And in a case, any two like charges. So if I want to decrease the potential energy, objects that attract each other coming together. So if I take those two objects that attract each other and I start to push them together, that's actually going to decrease the potential energy. Okay. So if I just let the book fall to the floor, it's going to decrease its potential energy. The north and south poles of the magnets, we get them closer together, it's going to decrease the potential energy. And again, the opposite charges decreasing that potential energy. Objects that repel each other move apart. So now I'm going to take those same pole magnets south to south, and instead of trying to push them together, I'm going to start to pull them apart. Okay, that's going to decrease the potential energy. Okay, spring being released, that's going to decrease the potential energy. And again, we can look at two like charges. All right, so which of the following then represents a decrease in the potential energy of a system? All right, hopefully you picked a ball rolling downhill. So as the ball is going down the hill, the potential energy is decreasing, right? Now, we might recall potential energy and kinetic energy are linked together, right? So if the potential energy is going down, we know the kinetic energy has got to be going up, right? All right, which of the following represents an increase in the potential energy of the system? So we have sodium breaking apart to two opposite charges. We have a periodic table falls off the wall. We have calcium 2 plus gaining 2 electrons, a firecracker exploding, and then burning gasoline. Which of the following represents an increase in potential energy? Hopefully you've picked A here, right? An increase in potential energy. We're taking something that's neutral and taking those opposite charges and pulling them apart. That's going to increase the potential energy because they want to come together, right? All right, next topic is the law of conservation of energy. Energy can neither be created nor destroyed. We can, however, convert from one form to another. Now, the total energy of the universe then has to be constant. That would be the overarching idea here. So your total energy then is going to equal your potential energy plus your kinetic energy. So we can convert back and forth between these two, and in theory, there's never any loss. And that's true if we're looking at the entire universe. Obviously, we're going to define systems, and as we look at systems, we're going to make some assumptions. Okay. So as we go through the math of these things, what are the units you're going to be looking for? Typically, we work with the joule. That's a capital J. Okay, so kinetic energy possessed by 2 kilograms of an object moving at a speed of 1 meter per second would be a joule. And so we can further deviate that joule into kilogram meter squared per second squared. Okay, and again, just derivation of units here. You might have seen this in a physics class. If you haven't taken Physics 1, Physics 2 yet, I'm sure you'll revisit these units when you go to look at energy. Now, if calculated value is greater than 1,000 joules, we will use kilojoules, right? And so it's a metric unit. So 1 kilojoule would be 1,000 joules, right? So a kilojoule is 1,000 joules. Another unit of energy we'll see is the calorie. Now, calories are defined by the energy needed to raise the temperature of 1 gram of water by 1 degree Celsius. And so we can convert back and forth between calories and joules. That's going to be 4.184 joules, and this is an exact value. And of course, if you don't recall, what that means is that when we look at our significant figures, if we convert between calories and joules, it will not impact the number of sig figs. Okay, so there's no impact here. We can convert exactly. And of course, calories are also a metric unit. And so we can do 1 kcal is 1,000 calories. Or if you prefer, 1 kcal would be 4.184 kilojoules. Now, this little calorie is not the same as a nutritional calorie. So our food calories are going to be a big C, right? So nutritional calorie is CAL with a capital C. Note the capital C, right? That's the big difference between the two. 1 food calorie is the same as 1,000 little calories. So 1 food cal then is actually 1 kcal. And of course, we already said 1 kcal then is 4.184 kilojoules. All right, so your turn then. Which is a unit of energy? Pascal, Newton, joule, watt, or ampere, and you better pick joule. All right. Convert 175.2 kilojoules into nutritional calories. 175.2 kJ into nutritional calories. And hopefully you got 41.87 here. And the way you would do that is take 175.2, divide it by 4.184 kilojoules. That will convert to kcals. And then we know it's 1 to 1, right? 1 kcal would be 1 food calorie. Kilojoules will cancel out, kcals will cancel out, and so we end up with 41.87 calories. All right, convert 57.9 kilojoules into calories. And hopefully here you got 13.8 kcals. Here we'll take 57.9 kilojoules, again convert it to joules, and then convert that to calories. All right, now you could have done kilojoules to kilocalories and then kilocalories to calories. That would have been fine as well. Mathematically would have been the same thing. All right. And then we can convert that back to kcals if we want. So you could have done this in one step or several. Your choice, depending on what units you're comfortable with. All right, so temperature versus heat. The temperature is the proportional to average kinetic energy of an object's particles. So we've already seen this. We know the particles are moving around, and temperature is proportional to that. So higher average kinetic energy is going to mean a higher temperature. That means faster moving particles. Right? So if I slow those particles down, we should see the temperature decrease. Or a lot of times what we'll do is decrease the temperature, and of course that will in turn slow the particles down. So what's the difference then? What is heat? Heat is the total amount of energy transferred between the objects. Now temperature and heat are related. Okay, that's going to be the key here. We can get an idea of the heat based upon temperature. Heat transfer is caused by a temperature difference. So if we see a temperature difference, that would be a calculation for the heat. Now heat always passes spontaneously from warmer objects to cooler objects. Okay, so the heat is always moving to the cool. Okay, and of course the heat will transfer until both are the same temperature. Now we'll show this with a sign. We'll get into the details here in a few minutes. But you can always think of it as, when you open the door in the wintertime, you're letting the heat out. Okay, now in the summertime, if you leave the door open, you're now letting the heat in, right? So the heat is always moving from the hot to the cool. All right, so heat transfer then, hot and cold objects placed in contact. Basically what starts to happen is you have the hot and you have the cold. And of course the hot will start to slow down, the cool will start to speed up until everybody is the same. Okay, so molecules in a hot object are moving faster. The kinetic energy transfer from hot to cold, so the hot ones will appear to slow down. And of course the cooler ones will appear to speed up until they're all moving the same. Okay, that's sort of the idea here. And that means, of course, if they're all moving the same, the temperature then would also be the same. All right, so heat. We're going to pour hot coffee into a cold cup. The heat then is flowing from the hot coffee to the cold cup. Faster coffee molecules bump into the wall of the cup. That's going to be a transfer of kinetic energy. And of course, if you have had your physics class, you may remember elastic collisions and inelastic collisions, right? So we're going to have a transfer, two things hitting each other. That energy is transferred to the second object, right? Eventually, the cup and the coffee will reach the same temperature, and we call that a thermal equilibrium. So in both the cup and the coffee are at the same average kinetic energy and the same temperature, that would be thermal equilibrium. Energy transferred through heat comes from objects' internal energy. Okay, so what is internal energy? Well, that's the sum of all of the energies of particles in the system. So E is actually going to represent the total energy of the system, which we know comes from the potential energy and the kinetic energy. So a change in internal energy then, delta E, would be equal to E final minus E initial. And of course that triangle just simply means there's change. Final minus initial, we always write change as final minus initial. which means what we can actually measure is going to be the temperature changes, which is what's going to give us the energy change. So we want to know the change in energy associated with any given process. So delta E then, change in internal energy for a reaction, means we're looking at reactants going to products, which means we have the delta E for the products minus the energy of the reactants. Now, we can use to do something useful here, right? From the energy change between products and reactants, what we can look at is work and heat. How much work is being done by the system and how much heat is coming off of or going into the system. If the system absorbs energy during the reaction, then the energy coming into the system is going to have a positive sign. Okay, so if the system absorbs energy, then it's going to have a positive sign. It means energy is going to be positive. The final energy then is greater than the initial energy. Photosynthesis or charging a battery would be this process. So if I need to charge my cell phone, then that's what I'm going to be doing, right? The final energy is going to be greater than the initial energy, and I'm going to see that in my battery. So as the system absorbs energy, which means we're increasing our potential energy. And of course, in the terms of our cell phone, that means we'll be able to use it later because it still has a charge. All right, kinetic molecular theory. This is going to carry through to gases as well. There's some things that molecular theory will tell us. Temperature means it's going to be related to the average kinetic energy of the particles in the object, which means we're looking at how they're moving around, right? The internal energy is related to the average total kinetic energy. Now, this will include your molecular potential energy. So your average kinetic energy then is going to imply a distribution of kinetic energy among the molecules in the object. So basically what we're saying then is that the temperature is related to the kinetic energy of the particles in the object, and the internal energy is related to the total molecular kinetic energy, which includes the potential energies. So in other words, if there's any reactions within the molecule, if we have a positive and negative ends, so a polar molecule, let's say, the average kinetic energy implies the distribution of those energies among the molecules in the object. So we're saying that if my table has energy and its kinetic energy, its kinetic molecular energy is across the entire table on the molecular scale. So all the molecules are averaging out to the same speed and temperature. Okay. Temperature and average kinetic energy. So in a large collection of gas molecules, now this is gas, not solid, right? So I pointed out to my table. Now in a gas, there's going to be a wide distribution of that energy, right? A wide distribution. So you have all these little particles moving, and what we're saying is if I were to stop and look at each particle, there's going to be a huge distribution here. We're going to have a small number with actually no kinetic energy. So in a gas, almost none of the molecules are sitting still. They're all moving, which means none of them are going to have an overall kinetic energy of 0. Now, if we look at the pinpoint time frame of a collision, then you get a momentary stop of that molecule's motion. That's where you will have some Ke equals 0. So if I freeze time, then there will be 1 or 2 molecules maybe that have a 0 kinetic energy. It's still going to be a very small number. Now, on the other end of that, we're also going to have a very small number with a very high Ke, right? Again, it's a huge distribution. Most molecules will have the intermediate Kes, and that's what we would expect. So we're going to have a curve out of this, right? So collisions tend to average the kinetic energies. The result then is that distribution. So again, we can draw a curve out here. And so if we look at a curve, so here's the lower temperature, we get a more even distribution, right? Now they still have some ones that are going kind of fast. We still have a few at 0, but the majority of them are in a small little area here. Now if I speed that up or otherwise give a higher temperature, notice the distribution kind of averages out more and becomes even more distributed across this whole curve, right? All right, so temperature then, the average Ke of all atoms and molecules in the object. We're looking at the average speed of the particles. And typically when we're looking at this, we're looking at Kelvin temperatures. So if you don't remember your Kelvin temperature scale, Kelvin is going to be equal to degrees C plus 273. Okay, we want to be on the absolute scale when we're looking at kinetic energy. So the temperature then in Kelvin is proportionate to the average Ke, which of course is the 1/2 mv squared. Okay. Now at a higher temperature, most molecules moving at a higher average speed. Cold object, you're going to have that smaller average. We pointed that out. Hot object, you're going to have a larger average. So note at 0 Kelvin, Ke would be equal to 0, so your velocity would be equal to 0. So in other words, we're saying the molecules will stop moving at 0 Kelvin. Okay. You can get into some theory there if you want. Not going to do that in the video pieces here, but if you ever want to ask me questions about it, feel free. All right, kinetic theory for liquids and solids. Atoms and molecules in liquids and solids are also constantly moving, but particles of solids will jiggle and vibrate. So they're not actually moving, they're just shaking. Okay. Distributions of the Kes then in particles for gases, liquids, and solids are the same at same temperatures. So at the same temperature, gas, liquid, and solid will have the same average kinetic energy, but very different potential energies. All right, so which statement about kinetic energy is true? Atoms are molecules and gases, liquids and solids possess Ke since they are all in constant motion. At the same temperature, gases, liquids, and solids all have different kinetic energy distributions. Molecules and gases are in constant motion, while molecules and solids are not. Molecules and gases and liquids are in constant motion, while molecules and solids are not. As the temperature increases, molecules move more slowly. All right, so we know we can eliminate C, D, and E. They all make no sense. A and B, let's see. A, atoms of the molecules and gases, liquids and solids possess Ke, since they are all in constant motion. That sounds pretty true. At the same temperature, gases, liquids, and solids all have different kinetic energy distributions. And of course, we just said that's not true, which means A has to be the right answer. All right, I think that's going to end segment 1. Next, we're going to start to look at delta E and get into the products and reactants. And we'll start to look at the states of the systems. We'll define some systems, and we'll talk about state functions. So hopefully, you're not too bogged down in theories here, and you're trying to wrap your head around some of these concepts. They can be a little difficult. All I can tell you then is look over it, ask questions, shoot me some emails if you have questions about it. I know it can get confusing. Take your time and just sort of logically work through it. All right, stay tuned for segment 2.